Hey guys, welcome to video 50. Today we're going to shift gears a bit and talk about the ubiquitous 555 timer. And in particular, I'm going to derive the timing equations for this thing. Alright, so starting on the left here, we've got the pinout and a picture of the dip, dual inline pin package. And on the right is the equivalent schematic that you would find on the data sheet for this device. Now, let's just take a quick run through of what we've got here. I'm going to start with this voltage divider, 3 equal value resistors. They're all 5K ohms, but they're going to divide the power supply voltage evenly so that at this node we've got 1/3 VCC, at this node we've got 2/3 VCC. And these are used as reference voltages for these two comparators. This is the threshold comparator used to reset this latch. This is the trigger comparator used to set the latch. The output is taken from the Q0 pin, but it's inverted and buffered so that the output here at pin 3 is really the same state as the Q output of this latch. The Q0 output is also used to control this discharge transistor Q1. That's used to discharge an external timing capacitor here. The other couple inputs, they're used to configure this thing either as a one-shot, that is a monostable multivibrator, or as a square wave oscillator, otherwise known as an astable multivibrator. We'll talk more about these on the next slide, but pin 5 is used to implement frequency modulation or pulse modulation. We're not going to worry about that today. As far as the power supply goes, it can vary anywhere from 4.5 to 18 volts, and the output can source or sink up to plus or minus 200 milliamps. So this is a pretty high current device compared to most devices you're going to see in this 8-pin dip. All right, let's go on over to the next slide and look at how this thing is used as an astable multivibrator. All right, so to configure the 555 as an astable multivibrator, we add these 3 external components, R1, R2, and C1. Over here I've added a load resistor that's referred to ground. You could also have RL referred to the power supply rail VCC, but we're going to go with the standard positioning here. Typically the output waveform at pin 3 is going to be a rectangular pulse train as we have shown here, and if you look on the data sheet you'll find all these equations for the various pulse parameters. F is the frequency or pulse repetition rate. T sub H is the time the waveform is high. T sub L is the time that the output is low. And D is the duty cycle of the waveform. That's the ratio of T sub H to the period T. And that tells us the average DC value of this waveform. Now let's take a look at what's going on inside the circuit. As soon as we apply VCC, we're establishing these reference voltages, 2/3 VCC at this node, 1/3 VCC at this node. Initially the capacitor is discharged, so VC1 is 0 volts. All right, now the output of the upper comparator is 0. The output of the lower comparator is 1, so we're setting the output latch. Q is high, the output is high, and Q0 is low, so this transistor is in cutoff. The capacitor is charging through R1 and R2, so the charging time constant is R1 plus R2 times C1. All right, now, as the voltage across C1 increases, it exceeds VCC over 3, but that just makes the output of this bottom comparator go low. The output latch just holds its present state, which is high, and the capacitor continues charging. Eventually, VC1 exceeds 2/3 VCC, which gives the reset command to the output latch. So Q goes low, Q0 goes high, turning on this transistor Q1, and that begins discharging the capacitor through R2. So the discharge time constant is R2 times C1. All right, so what we've got is tau charge equals R1 plus R2 times C1, and tau discharge equals R2 times C1. All right, and we're going to use these time constants to derive these equations next. Okay, so here I've redrawn the 555 in a way that you're probably more likely to see it on a schematic without all the internal details cluttering things up. Initially, we're going to be charging C1, and it's going to follow along this blue curve. The capacitor voltage is equal to VCC times 1 minus e to the negative t over the charge time constant. If you need a refresher on the charge and discharge characteristics of capacitors, go back to video 10 where we discuss those details. Remember, as long as the capacitor is charging, the output of the 555 is high. All right, so once the capacitor voltage exceeds 2/3 VCC, the output toggles low, and the discharge pin shorts this node to ground, so C1 begins discharging through R2, and the capacitor voltage follows along this green curve. All right, once the capacitor voltage drops below 1/3 VCC, the output switches back high, the discharge pin becomes an open circuit, and the capacitor again charges through R1 and R2 following this sort of curve, again hitting this other threshold where we change states, and so on and so on. So this is the waveform we'll see across the capacitor once we're in a steady state oscillatory mode. All right, now what we're going to do is solve these equations for various times on this graph, okay? In particular, we're going to be looking at the time it takes for the voltage to reach 2/3 VCC and 1/3 VCC, all right? Then we're going to look at the time it takes to drop from 2/3 to 1/3. And some useful identities in order to do this work are given down below here. So you might find these worth keeping handy for the following analysis. All right, now let's go on over. I've redrawn these waveforms in a much neater fashion, and what we're going to do first is find the time it takes for the capacitor voltage to go from 0 to 2/3 VCC. That's T3. All right, so the equation we're working with is 2 VCC over 3 is equal to VCC times 1 minus e to the negative t, which would be T3, over the charging time constant. I'll just call that tau sub c. All right, so we're going to solve this for T3. All right, so first thing we're going to do is divide both sides by VCC, and that cancels VCC from the equation. And that's one of the nice things about the 555 timer is its frequency and timing relationships are independent of the power supply because that cancels out. But anyway, what we get is 2 over 3 equals 1 minus e to the negative T3 over the charging time constant. All right, now we're going to subtract 1 from both sides. So 2/3 minus 1 is negative 1/3. And we'll just get rid of the negative signs by calling it positive 1/3. So we get 1/3 equals e to the negative T3 over the charging time constant. All right, now we want to get rid of the exponent, so we'll take the natural log of both sides. So we've got natural log of 1/3 equals negative T3 over tau sub c. And we're going to multiply both sides by the charging time constant to get T3. So charging time constant times the natural log of 1/3 is equal to negative T3. And if we want to get rid of this negative sign, we can just flip over this fraction, and we get T3 equals charging time constant times the natural log of 3. Okay, sorry about that little temporal glitch. I wanted to move these equations over to make some room here. What we're going to do next is determine T1, that is the time it takes the cap to charge from 0 to 1/3 VCC. We're going to follow essentially the same procedure, so if you'd like to try it first, pause here and go ahead and do that. Otherwise, here we go. We've got, in this case, VCC over 3 is equal to VCC times 1 minus e to the negative t1 over the charging time constant. All right, again, dividing both sides by VCC eliminates that constant, making this thing independent of the supply voltage. So we get 1/3 equals 1 minus e to the negative t1 over charge time constant. Subtracting 1 from both sides, 1/3 minus 1 is negative 2/3. Eliminating the negative sign, we get 2 over 3 equals e to the negative t1 over the charging time constant. Taking the natural log of both sides, ln of 2/3 is equal to negative t1 over tau sub c. And again, multiplying by tau sub c, we get tau c times ln 2 over 3 equals negative t1, and again, to get rid of the negative sign, I can just flip over the fraction in the logarithm, and we get t1 equals charging time constant times the natural log of 3 over 2. Okay, now remember what we're really after here is T2. That's the T sub H for the continuous pulse train. So we're going to have to subtract T1 from T3 to get that. So let's do a little housekeeping here. I'm going to clean up my workspace, and I'm going to keep my two end results because otherwise I'd probably forget them. And let's put them up top. And here we go. So now we've got T sub H, the high output time, is equal to T2, which equals T3 minus T1. Okay, and that's time constant charge times the natural log of 3 minus time constant charging times the natural log of 3 over 2. All right, we're going to factor the time constant out of here, so that gives us tau sub c times the natural log of 3 minus the natural log of 3 over 2. And basically what we have here is the natural log of x minus the natural log of y, which equals the natural log of x over y. So we've got the time constant times the natural log of 3 times the reciprocal 2 over 3. The 3's cancel, and we get T sub H equals charging time constant times the natural log of 2. All right, and normally we'd write this in terms of circuit components, so we'd probably write this as R1 plus R2 times C1 times the natural log of 2. And let's see what the natural log of 2 is. So 2 ln, that's 0.693, and that's exactly what you've got on the data sheets. Okay, this is 0.693. All right, now our next step is to determine T4. All right, I'm going to clear off my workspace here, but first let me rewrite this equation up here as T sub H equals 0.693 times R1 plus R2 times C1. Okay, and now we're going to work with the discharge equation for a capacitor, which says that V sub C equals V naught times e to the negative t over tau. And in this case, V sub C is the value we're approaching, that is VCC over 3. V naught, the initial value, is 2 VCC over 3. And that's times e to the negative t4 divided by the discharge time constant. Okay, so what we're going to do next is divide both sides by 2 VCC over 3, or multiply by the reciprocal, so that gives us VCC over 3 times 3 over 2 VCC equals e to the negative t4 over tau sub d. All right, now we're going to cancel the 3's and the VCC, and that gives us 1/2 equals e to the negative t4 over the discharge time constant, taking the log of both sides. Natural log of 1/2 equals negative t4 over tau sub d, multiplying by tau sub d, tau d times the log of 1/2 equals negative t sub 4. And finally, getting rid of the negative sign by inverting this fraction, we end up with t4, which is also the discharge time. So let's write t sub, or the low time actually, is equal to the discharge time constant times the natural log of 2. And again, the natural log of 2 is 0.693 approximately, so there is our low time. T sub h, T sub L equals 0.693 times R2 times C1. All right, and there we go. Those are our two primary equations for this circuit. And now the last thing we're going to do is put this together to get the oscillation frequency equation. So let me clear the decks here, and we're almost there. What we've got is the total period of the signal t is equal to t sub h plus t sub L. So we're going to add these two equations together, and I'm going to leave it to you guys to show that that works out to be 0.693 times R1 plus 2 R2 times C1, and that makes sense because we're charging through R1 plus R2 and discharging only through R2, so it should appear here twice. But anyway, taking the reciprocal, it works out then that our frequency of oscillation is equal to 1 over 0.693. That would be approximately 1.44, which is what we see on the data sheet, divided by C1 times R1 plus 2 times R2. And there we go. There are our equations describing the oscillation frequency for the 555 timer when it's set up as an Astable multivibrator. And we'll talk more about the 555 in other videos when we use it as a building block, but I thought it was an interesting exercise to show where these constants come from, and hope you enjoyed it. I'll see you guys next time around.